Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Well, we have at last come to the final act of this course in group theory. That is, unless I decide to add some more lectures later on. And that is to determine or characterize all groups of order 15 or less. As I mentioned earlier, some of these orders are readily dispatched. For example, any group of prime order is cyclic, so we don't need to worry about those. We can concentrate on the composite orders. And I'm going to leave the case of groups of order 4 or 6 as exercises. The general plan in such an undertaking as this is to break the search for groups of a given order into cases based on one or more parameters, such as, for example, the maximum element order in the group. The hope is that each case will lead to a group template that either uniquely specifies a specific group that has the properties we're looking for, or the template is invalid, in which case we don't have to worry about it. And as we have seen, normal subgroups provide a very powerful tool because they lead to commutativity rules that can greatly simplify the characterization. So, here we go. The first order that is not prime and is not 4 or 6, the ones I left for exercises, is groups of order 8. So let G be a group of order 8. As is often the case, the extreme cases are the simplest to deal with, so let's look at them. And we're going to characterize, or we're going to break the analysis into cases based on the maximum element order. If that is 8, then the group is cyclic, so that's easy. If there's an element of order 8 in a group of order 8, then we know the group is cyclic. At the other extreme, if the maximum element order of the group is 2, then every non-identity element is an involution, order 2, and so we proved it a long time ago. Actually, I think I left it as an exercise that G would be abelian. It's a one-line proof. So in this case, if A, B, and C are distinct involutions in G, and if C is not equal to AB, then this subgroup, C2A set product with C2B, has size 4. Remember, the group's abelian, so this is a subgroup. And it is essentially disjoint from C2 of C, the subgroup generated by C. These are little 2-element subgroups, all 3 of them. And so this subgroup has size 8, 2 times 2 times 2. And therefore it is the entire group. Everything's abelian. These 3 subgroups are strongly, essentially disjoint. That was the purpose of this condition, C is not equal to AB, which implies that A is not equal to BC and B is not equal to AC, and that's where you get strong essential disjointness. And so this is an internal direct sum, but it's often nice to characterize these groups with external direct sums. So G must be isomorphic to this external direct sum. or direct product. The only possibility left, which is the hard one, is that the maximum element order of G is 4. Okay. So G contains an element of order 4, but no element of order 8. If A is the element of order 4, then this subgroup has order 4, so it's a gigantic subgroup of G, and therefore it's normal in G. So we have, in this case, found a normal subgroup, and that's going to be a big help. In particular, if B is an element that is not in the subgroup, and we conjugate A by B, we must get another element in the normal subgroup, cyclic subgroup generated by A, so it's got to be a power of A. And that power must be 1, 2, or 3, because A has order 4. But conjugation preserves order. So if A has order 4, A to the K has to have order 4. But A squared has order 2, since A has order 4. So that eliminates this possibility, and the only possibilities we have left for K are 1 and 3. And of course, when K is 1, this says that A and B commute, and the group will then be abelian. And since it has an element of order 4 and an element of order 2 that is not in the subgroup generated by the element of order 4, G must be isomorphic to C4 direct product C2. All we are left with then is the case K equals 3 in this commutativity rule. To find an appropriate template for G, in other words, to describe enough properties of G so that we have a template that is satisfied by a unique group, and then we can say this is the only group left, we need a second generator. All we have so far is the element of order 4, which generates a subgroup of order 4. We need another element outside of that subgroup. But there are possibilities here. There might be such an element, which I'm calling B, of order 2, or there might not be. All the elements outside of this subgroup may have order 4. That still fits the case we're studying where the maximum element order is 4. So we need 2 subcases. Okay. This is typical. The analysis breaks up into many different cases. So let's attack this case. Maximum element order is 4, and G has an element B, not in the subgroup generated by the element of order 4, and B has order 2. So, okay. So we're supposing B is not in this subgroup of order 4 and has an element of order 2. And K is equal to 3, because we've eliminated the K equals 1 case already. That's the abelian case. In this situation, the group G is generated by A and B because the subgroup generated by A is gigantic. Anything bigger will have to be all of G, B is not in this subgroup, so the subgroup generated by both A and B is strictly bigger than the gigantic subgroup, therefore it's the whole group. And the group has order 8, that's where we started. Order of A is 4, order of B is 2, and this is the commutativity rule. So the group, in this case, maximum element order 4, there exists an element B outside of that, of the subgroup of order 4 that has order 2. G fits this template. But any group that fits this template will have order 8. It will have maximum element order 4. It will have an element of order 2 not in the subgroup generated by the element, or an element of order 4. And it satisfies this commutativity rule. Okay, so we have a biconditional, and G, therefore G does exist, and it is the unique group that fits this template. This is a dihedral template, D8. So G is isomorphic to D8, the dihedral group, in this case. We knew the dihedral group had to show up on this list somewhere because we're searching for all groups of order 8, and this is where it shows up. The issue is, could there be another group of order 8 that has maximum element order 4 and an element B outside of this gigantic subgroup that has order 2? Well, the answer is no, because such a group has to fit this template. And this template is a standard template, so it defines a unique group. The final case we have to deal with is maximum element order 4, and all the elements B that are not in this subgroup have order 4. Okay. Notice that B can't be the identity because the identity is in this subgroup. So that's the situation we have to deal with now. Both of these subgroups, therefore, have order 4. B is an arbitrary element that's not in this subgroup. Remember, the subgroup generated by A we set quite early in this discussion up here in this main case, max element order 4, we chose an element A of order 4. That applies to all the subcases. Okay. So these two cyclic subgroups have order 4. B squared has order 2. Okay. And since all elements outside of the gigantic subgroup have order 4, B squared has to be in the subgroup generated by A. But this is a cyclic subgroup of order 4 generated by A. The only element of order 2 is A squared. So B squared equals A squared. And since B was an arbitrary element not in this gigantic subgroup, we have shown that the square of every element outside of this subgroup, actually we have to be a little careful, every element outside of the subgroup, its square is equal to A squared. So if you square all the elements that don't belong to this subgroup, you get all you get is A squared. Okay. So A squared equals B squared. So and k is equal to 3. So this group, if it exists, is generated by A and B for the same reason that as in the previous case, has order 8. The two generators have order 4. We have a squared equals b squared, and we have ba equals a cubed b. This is the quaternion template. You can check back in the book for that. Okay. It's hard to remember all these templates. Don't expect to remember these templates, quaternion, dihedral, and so on. You may have to look them up. If you use them a lot, you tend to remember them, but then when you stop using them, you tend to forget. At least that's my experience. And so any group that has maximum element order 4, a group of order 8, that has maximum element order 4 and has this property will have to fit this template and be quaternion. But the quaternion group does have this property. So we have completed the analysis of groups of order 8. It wasn't all that easy, and it's only order 8. It took 3 main cases, one of which had 2 subcases. Okay. So here's the collection then. Was it 3 main cases or was it 4? No, it was 3. So there were 5 groups, 3 of which are abelian. And since we studied the fundamental theorem for abelian groups, the characterization of finite abelian groups, we know that these are the 3 abelian groups of order 8 and they're non-isomorphic. So we could have just simply said that. But I wanted to go through the analysis in detail so you get used to this process. Okay, so these are the 3 abelian groups, and then there is the dihedral group and the quaternion group. And we have shown that this is a complete list of the groups of order 8. We can take a little breather here. The groups of order 9, since 9 is 3 squared, we know that any group of order p squared, where p is prime, is abelian. And so then we can look at the multiset of elementary divisors. We either have a single elementary divisor, 9, in which case we have the cyclic group C9, or we have 2 elementary divisors. One's 3 and the other's 3. The product has to be 9. We have C3 direct product with C3. This is abelian, but it's not cyclic because it has no element of order 9. These are not relatively prime, 3 and 3. And so a generator here times a generator here does not necessarily have, and in fact does not have, order 3 times 3 or 9. So if this was a 3 and this was a 5, that would be a different story. This would have order 15 and then be cyclic. Groups of order 10. 10 is 2 times 5, and 2 does divide 5 minus 1. So theorem 13.19, the theorem concerning the groups of order PQ, of which this is 1, 2 times 5, shows that G is either cyclic, so it's a cyclic group of order 10, abelian of course, or G satisfies the valid template that looks like this. And this is the validity condition, the T condition. And it turns out that the T's that satisfy this are T equals 1 or T equals 4. For T equals 1, we're back to the abelian case. A and B commute. They have relatively prime orders. Their product has order 10, so we're back to a cyclic group, the same cyclic group, C10. But in the other case, t equals 4, we get a non-abelian group, and this is in fact, when t equals 4 here, this is in fact a dihedral template. It's the symmetries of the pentagon. Here is our rotation. It has order 5, so we've got a 5-sided figure. And here's our reflection. And BA equals A to the power, the power of the rotation minus 1, if you remember, that's 4B, or this could also be A inverse B. So for groups of order 10, we have the cyclic case, C10, isomorphic to C5, direct product C2, or we have the dihedral group. So there are two groups of order 10. There were two groups of order 9. There were 5 groups of order 8. Okay. We have 12 and 14 to go, but 12 is the most difficult case, so I'm going to do 14 next. It follows a similar pattern to what we just did. This is 2 times 7, and 2 does divide 7 minus 1, so again we have either a cyclic group, C14, or we have a group that fits this pattern, which is again dihedral. We've got our rotation, and we've got our reflection. So we got, again, two groups, C14 and D14. Groups of order 15, we had this, again, theorem 13.19. Now the 15 is what, 3 times 5, but 3 does not divide 5 minus 1, which is 4. So all these groups are cyclic. And all we are left with is the groups of order 12. As I have said, this is the trickiest case to classify. These groups have order 12, which is 2 squared times 3. So first we sort of marshal our forces by gathering what facts we do know about groups of order 12. We do have the cyclic group of order 12 and this abelian non-cyclic group of order 12. The alternating group A4 has order 12, D12, the dihedral group, symmetries of the hexagon, has order 12, and we have this dicyclic group we discussed in chapter 8, defined by this template, or equivalently by this standard template. Now I'm going to leave it as an exercise for you to show that no two of these groups on the list are isomorphic. And that may sound like a daunting problem, but it's not as bad as it sounds if you remember the concept of an isomorphism invariant. For example, none of the abelian groups, neither of the abelian groups, I should say, there's 2 of them, can be isomorphic to any of the non-abelian groups, because isomorphisms preserve abelianness. What we don't know at this moment is, are there any other groups of order 12 besides the 5 on this list? Well, we did see in example 13.11 that a group G of order 12 that is not isomorphic to A4 must have a normal CeLO 3 subgroup, Y3. So it's unique and normal. So assume then that G is a non-abelian group, so we've ruled out it being isomorphic to 1 or 2, and that it is not isomorphic to A4. What we need to show is that it must be isomorphic to either the dihedral group or the dicyclic group. Then we'll know there are no other groups of order 12 that are not isomorphic to something on this list. So the unique CeLO 3 subgroup has this form. It is a cyclic group of order 3 generated by an element A. And if Y2 is a CeLO 2 subgroup, it will have order 4 because that's the highest power of 2 that divides 12. Okay. And so there are two possibilities for a CeLO 2 subgroup. One possibility, and we're not saying those are unique. There may be many CeLO 2 subgroups, but all of them have to fit one of these two possibilities, either cyclic of order 4 or the Klein 4 group. Okay. Now, Y2 and Y3 are essentially disjoint because 2 and 3 are relatively prime, so their intersection's trivial. So the group G has one of the following two forms. Either it is C3 essentially disjoint set product with C4, and C4 generated by B here. That's this particular case where Y2 is cyclic of order 4. And in all cases, the CeLO 3 subgroup is normal. Okay. Or this is same as this, except instead of Y2 being cyclic of order 4, it's a Klein 4 group. The usual plan at a point like this is to see how A interacts with B, in this case, or how X and Y, how A interacts with X and Y in this case. And the tool we have is that Y3, C3 of A, is normal. And there are two cases then that we have to deal with. For this group, the conjugate of A by B, since A is normal, belongs to the cyclic subgroup generated by A. It can't be the identity, so it's either A or A squared. But in the former case, A and B commute, and so this is in fact an internal direct product. Both of these are normal. This is abelian, and it looks like this. Okay. In the latter case, so that's BAB inverse equals A squared, this group, which I'm calling G1 here, fits this standard template. It has order 12, element A has order 3, element B has order 4, and BA equals A squared B. This is the dicyclic group of order 12. So you'll have to go back to our discussion of the dicyclic group to check that template. For the final case, we want to show that this group, G2, which is C3A, essentially disjoint set product with the Klein 4 group, is either abelian or is dihedral. And those two are already on our list, and so that will complete the classification of groups of order 12, namely the 5 groups that we mentioned earlier. So to this end, we can use any of the dihedral templates that we discussed in Theorem 7.23 from Chapter 7. And this is one of them. It's a standard template. I'm sorry, this is not a standard template. This is the other template, T12, which is generated by 2 elements, alpha and beta. Group has order 12. The 2 elements are involutions, and their product has order 6, which is half the order of the group. In words, the dihedral group D12 is the unique group of order 12 that's generated by a pair of involutions whose product has order 6. Okay. So this should really be any. Now, since C3A is normal in G2, we know that the conjugate of A by X is in C3A, and the conjugate of A by Y is also in C3A. That means that this conjugate, XAX inverse, is either A or A squared, and similarly for YAY inverse, either A or A squared. So we need to consider some cases. If XAX inverse is A and YAY inverse is also A, that means that X and A commute and Y and A commute, but X and Y commute, so the 3 generators commute pairwise, and therefore the group is abelian. And so it's one of the 2 abelian groups we have in our list. And those are these 2 groups here, either C12 cyclic group or C3 direct product C2 direct product C2, which is abelian but not cyclic. This is the C3 direct product C4 case here. If XAX inverse is A, but YAY inverse is A squared, then we have to figure out how, so this is not abelian, we have to figure out how it fits into the dihedral template. So one way to approach this is just to compute the orders of some elements, not quite at random, but more or less, and see if we can spring out 2 involutions whose product has order 6. So we know that the order of X and the order of Y is 2, the order of A is 3. This just comes from the form of the group in this case. We know, and we can compute the order of AX because A and X commute. That's what this conjugation equation tells us. And their orders are relatively prime, 2 and 3, and so the order of the product is the product of the orders, which is 6. Same thing for the order of AY, 6. Okay. We still need, we're not done, we need to do more, so maybe we'll try AXY. Okay. If we square AXY, it looks like this, and now in here, lurking in here somewhere, we can, let's see, we can interchange A and X, we can get we need a YAY inverse, or YAY, because Y is an involution. So we can get it from here by interchanging X and Y. So we'll have AX, and then we will have YAYX. And YAYX is A squared X. Okay, so that's here. Why did I put this in between? Well, I think I'll take this out. Okay. And then X A squared X is A, let's see, where is that? X A squared X is A squared. And then there's still another A, so we get A cubed. But that's 1. So this element, AXY, since it's not the identity, has order 2. All right, so we've got this bit of information about element orders, and what we need are 2 involutions whose product has order 6. Well, here is something that has order 6, AX. So can we write AX as a product of 2 involutions? Well, AXY is an involution, and Y is an involution, and when you take their product, you get a Y squared, which is 1, so you will get AX, which has order 6. So we have 2 involutions whose product has order 6. But we do need to make sure that the elements alpha and beta generate the same group as G2 here. If we want G2 to fit the template, part of the template is that there are 2 generators, alpha and beta, that are involutions and whose product has order 6. Okay, but that's not a problem, and I'll let you sort that out. You can express A in terms of alpha and beta, X in terms of alpha beta, Y in terms of alpha beta, so they generate the same group. So G2 is generated by alpha beta. Alpha and beta are involutions. Their product has order 6. That's exactly what this says. Okay. And the group has order 12. Okay. Okay. So G2 fits the template T12, and so it is isomorphic to, or is a dihedral group. Now, if we reverse these two in another possibility that XAX inverse is A squared and YAY inverse is A, a similar argument is going to work. There's a symmetry here between X and Y, so we don't need to go through that argument separately. The final case is when AX A inverse is A squared and YAY inverse is A squared. As sometimes happens, or perhaps more than sometimes, we can reduce one case to another case, one hopefully we've already covered, and that's the case here. Okay, this is the Klein-4 group. It is the group generated by 2 involutions. It's a group of order 4. X and Y are involutions. The entire group, in fact, consists of 1 X, Y, and the product XY. This is the same group with an XY here in place of X, and I'll let you confirm that. If you take XY, which is now this element, and you use it to conjugate A, you will get A. So if we go back to case 2 here, if you replace this x by a different generator, xy, you in case 4 here, if you replace x by xy, this conjugation rule becomes this one. And the other stays the same. We haven't touched y, we haven't replaced it. And so this case reverts to case 2. Now one thing you might want to do is deal with this case in a different way. Do some hunting, just as we did for case 2. Check the orders of some elements. XY is an interesting element. It's an involution. It commutes with A, so it's in the center of the group. So anyway, you can play around with that if you want to. Okay. So that completes our characterization of the groups of order 12, and therefore we've completed our characterization of all groups of order 15 or less. So this is the last lecture in the series. It's possible at some later date I will add some auxiliary lectures, but at this point I'm planning on moving on. So I want to, if you've been with me through the whole series, I want to thank you. If you've bought my book, I want to especially thank you because I can use the support. And I will hopefully see you in another lecture series.